prove the sine rule, we will consider a perpendicular for this triangle. So let's look at a perpendicular from this point down to this line C. Let's call the length of the perpendicular H. Now let's look at this right angle triangle here that contains angle A. We know from basic trigonometry that the side opposite A is this side here, H, and the hypotenuse of this right angle triangle is B. So we know that the sine of A is opposite over hypotenuse, H over B. We can rewrite this to get H equals B sine A. Now let's look at this right angle triangle next to it that contains angle B. The side opposite B is also H, but the hypotenuse of this right angle triangle is A. Sine of B is opposite over hypotenuse. So from this we can get the perpendicular height, H equals A sine B. So B sine A and A sine B are both equal to H. That means that they must be equal to each other. So we can see that A sine B must equal B sine A. In order to show that A over sine A equals B over sine B, we need to divide both sides of this equation by sine A sine B. We can see that the sine B's cancel on the left hand side and the sine A's cancel on the right hand side, and we are left with A over sine A equals B over sine B. Now, what about showing that A over sine A equals B over sine B equals C over sine C? In practice, we don't use this third ratio. In practice, we just use these two. But let's just go through the proof of the complete sine rule. What we do is we draw in a different perpendicular. We can draw in this perpendicular. Now, I won't call this one small h, because it's going to have a different length from the previous perpendicular. So I'll just call this one y. So I've dropped the perpendicular from this point down to this side of the triangle. So we have two right angle triangles formed, and we can look at the sine of C and the sine of A. Well, the sine of C is the side opposite C in this small right angle triangle here. The side opposite C is y. Now what's the hypotenuse of this small right angle triangle? Well, the hypotenuse is the longest side, opposite the right angle, it's A. So from this we can see that the perpendicular is A multiplied by sine C. And then we go to this other right angle triangle next to it, which contains angle A. We see that the sine of angle A is the side opposite angle A, which is y, divided by the hypotenuse of this right angle triangle, which is C. So from this we get y equals C sine A. So A sine C and C sine A are both equal to y. They're both equal to the same thing, so they must be equal to each other. What we do is we divide both sides of this equation by sine A sine C. The sine C's cancel here and the sine A's cancel here. So now we've shown that A over sine A equals C over sine C, but we've already established that A over sine A equals B over sine B. So we see that both B over sine B and C over sine C are equal to the same thing, namely A over sine A. So that means that B over sine B must equal C over sine C. So that's the proof of the sine rule when A, B and C are acute angles. Now what about the situation where one of the angles of the triangles is obtuse? So let's suppose that angle C is obtuse. Well, only one angle can be obtuse because the three angles have to add up to 180 degrees. So we can't have two angles that are more than 90 degrees, because in that situation the three angles would add up to more than 180 degrees. Anyway, here's the picture. How are we going to consider the ratio C over sine C? how can we get the sine of angle C by referring to right angle triangles? Well, what we do is we extend this side here and consider this external angle of the triangle. Now this external angle is 180 degrees minus angle C. We consider this right angle triangle here got by getting the perpendicular height of the triangle using this side as base. So we have to extend this base, drop a perpendicular here whose height I'm calling H. Now let's look at the sine of angle C. Well, we know that for an obtuse angle, its sine is the same as the sine of the corresponding acute angle. So these two angles sum to 180 degrees. So the sine of C equals the sine of 180 minus C. You can go back to your unit circle to see that. We know that in this quadrant here, only the signs are positive. If you go through all the unit circle theory, you know that if we have an obtuse angle, its sine, say this angle here is A, then the sine of A is equal to the sine of this angle in here, which is 180 degrees minus A. This quadrant is called the S quadrant, which means that the sine of an angle between 90 and 180 degrees is positive. It's the same as the sine of this reference angle. So these two angles sum to 180 degrees. So anyway, that's the background. In this right angle triangle here, the sine of this angle is the side opposite this angle, which is H, divided by the hypotenuse, which is A. So from this we see that H is A multiplied by sine C. So we multiply A by sine C. But if we take a look at this larger right angle triangle, whose hypotenuse is C, the longest side is C, and consider angle A. The sine of angle A is the side opposite angle A. Well, the side opposite angle A is H in this larger right angle triangle. And the hypotenuse, the longest side, is C. From this we get H equals C sine A. So A sine C and C sine A are both equal to H. They're equal to the same thing, which means that they are equal to each other. So A sine C equals C sine A. And we just divide across by sine A sine C. Divide both sides by the same thing, sine A sine C, and we end up showing that A over sine A equals C over sine C. So we can see that the sine rule works for the situation where one of the angles is obtuse. To show that A over sine A equals B over sine B, we could use this perpendicular height here. So I won't go through that. That's similar to what we did earlier.